Mevrouw de rechter-magnificus, meneer de decaan, leden van het curatorium van de leerstoel Complexiteit voor Officiële Statistiek, bestuur van het Centraal Bureau voor de Statistiek, geachte collega-hoogleraren, zeer gewaardeerde toehouders. Through a combination of circumstances and personal preferences, I've conducted research on a variety of topics over the past decades. It has become a kind of smorgasbord, and I am pleased to invite you to the feast today through this public lesson. I hope you can enjoy it as much as I do. It is an important objective of the Complexity for Official Statistics Chair to build a bridge between Statistics Netherlands, CBS, my main employer, and the knowledge and techniques that are developed within the academic discipline of complex systems. I therefore think it makes sense to tell something about each of those two separately, official statistics and complex systems, and only then describe my vision of what the two have to do with each other. Before I get down to the task of doing all of that in a single public lesson, it is important that you know that I was trained as an astrophysicist, and that for years I've conducted research in theoretical or mathematical sub-areas within it. This means, among other things, that I tend to think that how long a phenomenon lasts, or process, is only meaningful in relation to another timescale belonging to a related or relevant other process. Now you are forewarned that I may take giant strides through the blink of an eye that is human history, without always making a distinction between a decade and a millennium. In addition, this background also means that my worldview revolves around physical processes and interactions rather than things. You may think that this mindset is not the best preparation for taking up employment at an agency whose task it is to count people and companies and categorize and describe their characteristics and neatly tabulate and publish the results. I hope I can convince you that this is an incomplete view of the purpose of a National Statistical Institute. Statistics Netherlands has now been in existence for about 122 years, and over the years it has started to keep track of and monitor more and more things that are important for public policy. Not only are data collected and published about the population, but also about health and security, about education and leisure activities, about the environment and all kinds of economic activity, both nationally and internationally. It is much more recent in origin that there is a further separation between the collection and publication of measurement data by Statistics Netherlands and the use of models calibrated on that data for calculating the potential consequences of public policy choices through the Bureau for Economic Policy Analysis, the CPB, and the even more recently established Institute for Social Research, SCP, and the Environmental Assessment Agency, PBL. It is debatable whether this division between Statistics Netherlands and CPB was partly motivated to demarcate territory between the then CBS Director General, Edenburg, on the one hand, and Jan Tinbergen on the other, who was working at Statistics Netherlands at the time. Tinbergen subsequently became the first director of the CPB and was later also the winner of the Swedish Riksbank Prize for Economics, a prize that is equated with the Nobel Prizes. However, there's also a substantive reason for making this separation. Just as a distinction is made between theoretical and experimental physics, in the case of the CBS-CPB distinction, this division explicitly prevents the impression that the measurement data might have been given a political slant. Such a separation also has drawbacks, but to explain them, I would first like to take you in the world of the science of complex systems. Language use in a technical context, sometimes condescendingly referred to as jargon, makes use of very precise definitions if all goes well. That may seem fussy, but it is really necessary to enable, for example, that redoing experiments or measurements is indeed carried out precisely and correctly. That reproducibility is fundamental and distinctive to real science. Technical language use therefore sometimes leads to misunderstandings if a certain word also has a daily and much less precisely defined use. The word complex in complex systems is unfortunately such a word. In everyday usage, it is often used as a synonym for complicated or even synonymous with incomprehensible. Then it can happen that poorly documented and unstructured computer code is described as complex when it is merely the result of bad habits and laziness. To paint a picture, I would like to give some analogies from nature that are expressions of complex systems before taking a deeper dive into a more abstract mathematical description. The first analogy is that of a termite mound. An individual termite is by itself an independent living organism. Considered as a unit among many members of the species, a single termite is not very intelligent. It reacts to external stimuli in quite restricted ways. Yet a large collection of termites is able to build structures on a scale that far exceeds their own size. And these are structures that also perform functions that allow a degree of control over the environment of that termite society, such as temperature control, which the single termite cannot possibly understand. Clearly, that termite society, the termite mound, is capable of behavior that does not follow trivially from the behavior of individual termites. The whole is more, can achieve more than the sum of its parts. The construction of termite mounds, or the patterns that form in murmurations of starlings, are an expression of complex systems. This is summarily referred to by the term emergent behavior. We can also descend in scale level to that of atoms and molecules. Even with just the elements hydrogen, carbon, nitrogen, oxygen, and phosphorus, it is possible to build a huge variety of molecules. If those molecules are strung together in long chains, they can start to behave like self-reproducing machines. At this scale level, it is indistinguishable whether we are looking inside humans or termites or petunias or whales. There is no external controlling principle or overarching organism that imposes an order of elements that is then reproduced. In fact, a long chain with the same sequence of elements can fold around in different ways and thus acquire different chemical properties. My colleague Professor Monaghan can explain this in far more glorious detail than I can. The possibility in itself that elements can form bonds naturally exists in the electron structure of individual atoms themselves. However, there are boundless possibilities to build structures out of this that don't even have to be chains. So whether and which chains are formed and how they fold is by no means fixed in the atoms. It is self-organizing behavior of the system. Self-organizing behaviors can also be found on other scales in nature, and they are not limited to the animal kingdom either. It only takes a short trip from here to the dunes to see that structures made up of loose grains of sand display certain patterns that do not follow trivially from the properties of those grains of sand. As the slope of a dune increases, the chance of larger and smaller cascades and streams of sand increases. These sand displacements make the dune slope smaller again. There's a feedback mechanism that ensures that dunes retain a certain shape and remain permanently in what is called a self-organized critical state. Another example of this are earthquakes. A geophysical rock stratum can be unstable from fractures, such as where continental plates meet, and from other natural causes. But fractures come in all sizes, from hundreds of kilometers to a few micrometers. There's a very broad spectrum. Those very small fractures will be described as brittle rocks, rather than fractures, but they are actually part of a continuum. If the pressure on that rock changes, for example, because of shifting overlying layers of earth, or because an internal pressure changes, such as when gas is extracted. It could mean that rock structure suddenly changes violently, resulting in an expanding wave movement, an earthquake. Because the faults are present over a wide spectrum of sizes, this can also be visualized with the aid of diagrams such as the Gutenberg-Richter plots that I'm showing here. What you see are counts of quakes of a certain magnitude on the Richter scale, in this case for the province of Groningen. Larger quakes are rarer than small quakes, so the counts decrease as the quake strength increases, more towards the right in the diagram. Of course, there's much more to say about the statistics of earthquakes in Groningen, but then I digress too much. What is important is really that this kind of shape is something that is quite universal in complex systems, power laws shape. I cannot resist the temptation to give you an example of things on an even larger scale. What you see here are large collections of stars. The photo on the left is a galaxy, number 74, from the catalogue originally prepared by a French astronomer, Charles Messier, who lived in the late 18th century, early 19th century. This photo of the object is of much more recent date than the mound. The photo on the right is object M3 from the same catalogue. And these type of objects are called globular clusters. Also a gravitationally bound collection of stars, but much smaller than a galaxy, and with a different history and structure. M74 is roughly comparable in size to our own galaxy, and our galaxy, and also M74, has quite a few satellite systems, such as this M3. What I want to do next is something that will appeal to all Statistics Netherlands staff among you, a census of the star population. I graphically represent the result of that census in the form that astronomers recognize as a Hertzsprung-Russell diagram. The picture on the right shows the result for M3. The vertical axis shows the intrinsic brightness of the stars, and on the horizontal axis is how astronomers measure color, which is a measurement of the surface temperature of the star, with hotter stars more to the left in the diagram. Every point in the diagram is a star, and you will probably notice that the points are not evenly distributed throughout the diagram. The greatest density of dots is distributed as a kind of a ribbon that runs from the bottom center of the term main sequence up to where it says red giant branch, and is then draped across the diagram to the left. I will not elaborate about the life course of stars, but what I do want to tell you is that within that ribbon, in the order I just used to describe the diagram, stars increase in mass, from less than one star of the Sun to a few dozen times that of the Sun. The count of the numbers of stars as a function of their mass, the distribution function for star mass, also shows a power law that says something about the self-regulating processes that determine the mass of stars when they are formed. I am cheating a bit because the diagram on the left is not the census for M74. Instead, it's the census of our own Milky Way, very similar to M74, where the Gaia satellite gives us enough precision measurements for roughly 1.3 billion stars. The differences in these two diagrams, the systematics revealed by this census, shows that the majority of stars in the globular cluster formed almost simultaneously, while galaxies have multiple generations of stars. That is, the star formation process has active periods and also less active periods. This too is an important aspect of complex systems. It may well be that a complex system does not have just one equilibrium. It can instead show periodic phenomena, or a few discrete quasi-equilibria between which it jumps from one to the other at unpredictable times. Okay. After this whirlwind of examples, I now come to the point that I want to take a step back and try to formulate a definition for a complex system. I hope it is clear that such a system consists of many parts and that have a certain degree of autonomous existence, such as termites or stars, but also form certain structures in each other's presence, such as termite mounds or galaxies. For the purposes of Statistics Netherlands, these autonomous units are people or companies, and the structures are Dutch society and the economy. As a system, they will exhibit certain characteristics such as emergent behavior and self-organization, and in determining distribution functions of properties, skewed power laws will be the rule rather than the exception. It may also be expected that in the time evolution of such systems, there will be sudden transitions, interspersed with longer periods of apparently stable equilibrium. It is also useful to take into account the timescales on which the units persist and how this relates to the timescales of interactions. If units mainly interact with a certain subset of other units over their entire lifespan, the system as a whole is relatively rigid, and it makes sense to use the methods and mathematics that are used for research into complex networks. That's the diagram on the left here. On the other hand, it is also possible that parts of a system have frequent but fleeting contact. In astronomy and in statistical physics, computers are usually used to perform many particle simulations of such systems. After many repetitions of simulations with slightly different initial conditions or adding noise, the statistical properties of the system are then mapped out. In computational social sciences, the equivalent is called agent-based modeling. Thus, this kind of simulation approach is not primarily to predict the future of a system, but to examine how model parameters, i.e. the properties of particles or agents, determine the behavior of the entire system. Sometimes it makes sense to describe a system hierarchically. Detailed modeling of interactions at the microscopic level, human to human or company to company, is abandoned, and in its place a much smaller system of blocks interacting with each other is modeled. Experience shows that there is a trade-off in the sense that the mathematical equations which calculate how a system behaves will receive more terms, and in particular non-linear terms, like the equations that I'm showing here. Since all three situations can occur in interactions between companies or interactions between people, my research on complex systems will therefore also have different lines. One for each of these approaches: the theory of complex networks, agent-based modeling, and dynamical system theory. So far, I have bravely resisted the temptation to switch from English and speak a language in which it is easier to be precise and unambiguous. I mean the language of equations and formulas, mathematics. I will try to maintain that, but I still need it every now and then, since I also want to be able to quantify the processes that I'm looking at. As soon as we want to measure these indicators in society or the economy and compare those measurements with explanatory models, it is necessary to convert the qualitative descriptions into numerical parameters and indicators. I just mentioned that in the line of dynamical systems research, the mathematical formulation of the model of reality will often consist of a set of coupled differential equations. The description of the system as separate elements with their interactions is often referred to as a microscopic approach. And once I start grouping those elements and modeling the interactions as interactions between groups, I have what is called a mesoscopic approach. Each group, each block in the dynamic system is fully described in this approach by a number of group properties. These are the dependent y variables in a model. For the sake of convenience, I will assume that these variables can take not only discrete values, but all values in an interval. Those properties can differ from block to block and can change over time. A change in time of a dependent variable is indicated as a rate or time derivative. Each of those time derivatives can be related to that set of variables themselves, or products thereof, or powers, or other nonlinear combinations. It is even possible that local spatial gradients play a role in the development of time, and therefore also derivatives with respect to a position x occur. In practice, this can take on a very complicated form, so it is not useful to specify this in more detail now. I just want to show you a few examples of what we can possibly expect to see happen. I think it is appropriate to show a specific equation whose solutions show something interesting and which will be very familiar to my mathematics colleagues in particular. That's this equation in the top left-hand corner. It is called the Korteweg-de Vries equation for one dependent variable which depends on time t and spatial coordinate x. There's a lot to say about this equation, but it really goes too far afield. The point here is that it is an example of the kind of equations with nonlinear terms that we will also distill from descriptions of interactions between groups of people or groups of companies. The interesting solutions of this particular equation are running waves over the coordinate x. These are generated spontaneously in the system, even from a smooth initial situation. And that a linear system will never do. It is also remarkable that two different wave solutions, which will have a different speed, can collide and emerge unscathed from that collision. That's in the top right-hand corner, depicted as a diagram. For linear equations, that's nothing special, but it is very unexpected for equations with nonlinear terms. These types of traveling wave solutions produced spontaneously in the system are referred to by the term soliton. A nice detail is that the real-world phenomenon was actually accurately described by a Scottish marine engineer, John Scott Russell, some 60 years before the mathematical equation and analysis was published. I would like to remind anyone who is wondering how this could be of importance to the field of activity of Statistics Netherlands that there are sufficient examples, even in recent history, of social or ideological groups and political parties in the Netherlands, which at first sight appear to be completely homogeneous and yet spontaneously undergo a schism and move apart in subgroups. At the very least, it is interesting to research the circumstances or characteristics of groups that influence the likelihood of schisms and social polarization. For a long time, it was common practice in both physics and economics to describe systems as equilibria and to approach changes over time as reversible processes. It is partly under the influence of Professor Ilya Prigogine that research into dissipative systems and systems that are far out of equilibrium has boomed. A beautiful and very simple example of the latter is the sudden formation of crystals in supercooled water. Under the right conditions, it is possible to cool water to well below 0 Celsius while still remaining liquid. A very minimal disturbance can suddenly trigger a transition in its system, and crystal formation occurs on a very short timescale. For this behavior too, an equation can be formulated that describes the time evolution of the relative proportion of water and ice crystals, which indeed include nonlinear terms. Much the same formalism has also been used to describe traffic congestion, where two phases, water and ice, are replaced by moving and stationary cars. We have probably all experienced sitting impatiently in a queue of stationary cars and finding that suddenly everything starts moving without any indications of what caused that traffic jam in the first place. Both are a manifestation of self-organizing behavior. In 1972, Herman, Lam and Prigogine showed that the statistics of journey times over certain routes in the US, UK and Australia, and the amount of time that cars had to stand still on those routes could be well explained by this model. The Netherlands not only has a high population density and therefore car density, logistics and freight transport by road play an important role in the Dutch economy. It is therefore good for policy making and planning in the field of road construction and the environment to know which parameters most effectively, favorably influence the flow of traffic. It is therefore obvious that values of precisely those parameters for traffic behavior in the Netherlands should be monitored. In the examples I discussed so far, the complex system spontaneously showed some unexpected behavior as a function of time, while the model parameters of those systems remained fixed values. If in a model for a complex system the parameter values are varied, the solutions of the model naturally change, but in many cases such changes can be regarded as gradual, continuous deformations. In some cases, however, something else happens. The example I want to quote here is the so-called logistic map. It is sometimes also referred to as the predator-prey equation, since it describes the precarious balance between predator and prey in a closed system. This again describes the time evolution of a system with a dependent variable x, but in discrete steps instead of as a continuous function of time. The single parameter r, that is in that equation there, controls the behavior of the system. When r is less than a certain limit, this x tends to a single equilibrium value as time goes by. However, as soon as that limiting value for r is exceeded, the behavior of the system changes abruptly. Instead of converging to a single equilibrium value, the x jumps back and forth between two different values. At the second, somewhat larger limiting value, the system again abruptly changes its behavior and jumps between four different values. These abrupt doublings of the number of values between which the system jumps, and this diagram shows the endpoint, so the final value, or final values. After a certain value of r, this x no longer shows any kind of periodic behavior. A diagram can be made of the equilibrium values, and that is shown here. And every splitting or fork in this graph is called a bifurcation. The exact order of values for x is extremely sensitive to the initial value of x. In mathematical terms, this is called a chaotic system. The behavior of model systems that bifurcate or become chaotic for a certain combination of parameters is known and well researched for many different systems, including the climate of our planet, and is certainly of importance for understanding our economy. One reason for this importance is fairly obvious. If an accepted economic model can display this type of behavior, it is of course important to determine from measurements what exactly the value of the crucial parameters is, because planning bureaus need the correct values of that parameter, for example. The second reason is less obvious. Statistics Netherlands publishes many indicators, including economic indicators, on a monthly or annual basis. That is, at discrete times. Not only the planning offices, but also other parties that themselves play an active role in the economy use these data to make estimates or predictions themselves. This means that decisions with economic consequences are also based on the time series published with a certain cadence. The example of the logistic map shows that if an unfortunate choice is made of the weight of the existing data in model predictions and the subsequent actions, the indicator in question can start to display chaotic, unpredictable behavior with potentially disastrous economic consequences. This picture is less far-fetched than it seems. Stock trading based on computer algorithms became fashionable in the 1990s. In the early days of these algorithmic trading systems, there were not enough security measures in place to limit the strength of possible feedback. It is likely that this contributed to the 2010 flash crash, and it may also have caused more variability, volatility in economic time series earlier on. I would like to add another mathematical concept, namely that of the dimension of objects or of spaces. I probably won't have to tell you that a point without dimensions has dimension 0 and a line has dimension 1. A plane or something in it, such as a circle, has dimension 2, and so on. I will not tease you with four-dimensional space-time and curvature tensors. I do want to show you remarkable objects which can be constructed recursively, for example, and recursive means by repeating a certain simple recipe of steps infinitely often. What I show you here are called the Sierpinski carpet on the top right and the Menger-Sierpinski sponge where in order to make these visualizations, the process has been stopped after a finite number of steps in the recursion. A tastier, real-life example is this Romanesco broccoli. There are many more variations of these types of objects associated with the names of famous mathematicians, such as Peano and Cantor and Mandelbrot. There are several ways to precisely determine the dimension of an object mathematically. The Hausdorff dimension is a well-known way, and that dimension is neatly integer for the more ordinary objects, but not for the whole carpet and sponge shown in the image. The Hausdorff dimension is fractional, which is where the name fractal for these types of objects originates. A few pictures ago, I showed the Lorentz butterfly. I will repeat it here. And that is the path in a three-dimensional space that the solution of a nonlinear dynamic system with three dependent variables over time follows. Obviously, that path isn't perfectly periodic, but it doesn't fill the whole space either. It's not uncommon for nonlinear dynamical systems to do such a thing. Therefore, it is technically called a strange attractor, and strange attractors have the property of having fractional dimensions. Within that strange attractor, the path does fill that particular subspace and thus has the characteristics of chaos, which is also called low-dimensional chaos. That brings me to the right-hand picture with a network. For the typical purposes of Statistics Netherlands, each circle in this diagram can represent a person or, for a different purpose, a company. The lines connect two circles if these two people or companies also know each other, do trade with each other. Statistics Netherlands has built up a network based on people who are related to each other according to the basic register of persons, parents, children, brothers, sisters, etc. And there are also, of course, other ways in which people could know each other that Statistics Netherlands cannot detect. Friends and acquaintances on social media platforms or from a neighborhood cafe or gym or music or hobby association are not stored in the Statistics Netherlands databases. Nor does Statistics Netherlands know that there are people that you see every morning when you're waiting for that train to work in the early morning and who, like you, are preparing for the day with a cup of coffee. The distribution function that describes how many people have a relationship with only one or two others, or with 5 or with 100 or more, can also be described with such a power law that I also showed before for earthquakes. It's of course not for nothing that I've placed this description of networks under the heading fractals, so you probably have already guessed. The exponent in that power law is something like a dimension of the network, and that dimension is fractional. The intention is that Statistics Netherlands will publish reliable new statistics that provide information about the statistical properties of relationships between people. An example are statistics on the geographic distance between the place of residence of adults and the place of residence of their elderly and vulnerable relatives, for which they may at some future time have to provide informal care. Not unimportant when publishing these new social network-based statistics is that this must be done under strict conditions of privacy protection, which has therefore also become the subject of Statistics Netherlands research projects. In the case of relationships between companies, less data are available to Statistics Netherlands than there are for people. There is a great importance for public policy and therefore for official statistics to know more about the connections between companies within the Dutch economy. Greater connectivity may mean, for example, that if a particular company ceases to exist, for whatever reason, there are other companies that can take over the role, and the system as a whole is therefore relatively resilient, and the flow of goods and services across that network remains stable. However, it can also mean that the bankruptcy of a particular company causes a whole cascade of bankruptcies through that network of associated companies. More concretely, Statistics Netherlands is currently investigating for a specific regional cluster of companies what dependencies between those companies play a role in facilitating a transition to using sustainable sources of energy. As I just indicated, it is already important for official statistics to determine properties of that set of relationships between persons or between companies. It is therefore a small step to not only want to map the networks themselves, but also to measure the behavior of dynamic processes on that network. How does the chance of cascades of bankruptcies depend on the connectivity of a business network? How quickly do innovations penetrate such a network? What is the probability that a healthier lifestyle is actually contagious across a social network, and how fast does that work? Does it also work with attitudes towards conspiracy theories or with the spread of infectious diseases? The short animation that I ran just now showed such a process taking place on a network. It's only a toy model. It has very simple rules. As you saw, the spheres change from black to red if they connected to a sphere that was already red. Then the color of the sphere slowly turns back again. Since this process only occurs when there is a connection, it is no surprise that the amount of connections will play a role in the speed at which red dots appear. But not only the average amount of connections will play a role in the speed at which red dots appear. If a cluster of points is interconnected but has no connections to the outside, there's no mechanism to get red dots within that cluster. So very subtle details in a network of contacts can have major consequences for distribution models. It's therefore important for public safety, for public health, and for a robust economy to know exactly which subtle properties of a network must be mapped. Complex networks are a good translation to mathematical objects and rules of how people or companies can form lasting relationships. In its most extreme form, all connections in the network are fixed, and research revolves around processes and signals that move through this system over those network connections. That is probably not a very realistic approach to reality. Not all contacts between people or companies are long-lasting. It is therefore desirable to be able to simulate more flexible systems, in which the timescale on which processes run through a system and the timescale on which connections appear or disappear in the network are more comparable. This requires different mathematical approaches than those whose timescales differ greatly, and thus also influences what statistics methods should measure in terms of society, when we translate those mathematical insights back into the field of visual statistics. That brings me into that third line of research, the particle simulations or agent-based models. As astrophysicists, among others, have long resorted to the use of simulations in which the particles are, for example, entire galaxies and the system, the large-scale structure of the universe. There are several reasons for resorting to this approach. An important reason is when little is known about the typical timescale of various interactions between the agents, or when those timescales are close together. In this case, it is more objective to specify the rules for interaction, as well as the rules necessary for the system to evolve one step ahead in time. It is then left to the computers to perform a new simulation, very often with slightly different initial conditions each time, so that one can draw statistical conclusions from the example of all of those simulations. Progress in this area also depends on faster computers and smarter computing algorithms. It is now within reach to conduct this type of research for models with tens of millions of agents at the same time. For me, the aim is to investigate the mechanisms underlying emergent social phenomena such as segregation and inequality. It is often said, and inappropriately on more than a few of those occasions, that society or the economy has become more complex over the past century. An example of change in a system that can genuinely lead to complexity is through specialization. When a company grows, individual sectors of that company can become increasingly separated. These individual units can even separate completely and then independently enter into associations with other companies. So that means that in the entire economic system, more autonomous units have appeared with interactions between some, but not all. Successively, mechanization, automation, and computerization of production processes have indeed resulted in much more specialization over the past century. In other cases, the system has always been complex, but its widespread recognition has originated more recently. An example of this are really the Sustainable Development Goals, which were drawn up on behalf of the United Nations in response to a report by famous economists Stiglitz, Sen, and Fitoussi. In the diagram, I highlight a few areas by way of illustration with which I certainly do not want to suggest that other goals in the SDGs are less important. What I want to point out is that economic activity has an impact on people's well-being, both favorable and unfavorable, on the living environment and the climate, and also on equality between people. And each of these also has an impact on each other and on economic activity. In recent years, economists have spoken of a worldwide slowdown in production growth. Since this is the collective economy of the whole world, that means that the system must be nonlinear. If all the interactions in the system were linear, this slowdown of growth would never occur. So there's a feedback in the system as well, and that means that you should expect that there is a power law behavior of units in terms of the amount of money that companies have, the amount of turnover, etc. So those skewed distributions of income and wealth that you actually see in the data, even in the most egalitarian countries, is at the very least an indication that social economic systems are in a self-organized critical state. So at the level of the United Nations, there's a recognition that these interactions are at least as important as subjects themselves. And within the Netherlands, attention is already being paid to this at public policy level by having the Monitor Brede Welvaart drawn up by Statistics Netherlands in collaboration with other partners, and discussing this in a separate session in Parliament. Another important alternative route is to test directly from time series whether correlation could also imply causation. In fact, the reverse is actually more feasible. Can a hypothetical causation mechanism be falsified using cross-correlation data? In the context of visual statistics, I've taken the first few small steps. There is a rather more famous recent Nobel Prize winner who has worked on this as well, and I expect a lot from my colleagues at the UvA to work on this too. Now, I'm almost ready to complete this public lesson, and there is one more concept that I would want to discuss, namely build that bridge between measuring and knowing, and that concept is ergodicity. Unfortunately, I'm very close to running out of my time, and I'm almost certain that I'm running out of your patience too. So I will skip a little bit of my presentation just to mention that if you take an expectation of an ensemble of simulations that is only produces the same thing as the evolution of a system over time if that system is ergodic. And there is no guarantee at all outside of physics that the systems that we're really interested in, people and companies, have that property of ergodicity. So we should be very careful when we use simulations and ensemble averages over simulations as a proxy for what the system will do as a function of time. Ik dank het college van bestuur van de Universiteit van Amsterdam, de decaan van de faculteit FNWI en de rector, en het CBS bestuur en curatorium voor deze leerstoel voor het in mij gestelde vertrouwen. I've had the privilege of doing research with many different people, all of whom I ought to thank. Science itself can be thought of as a complex system of scientists and interaction between them. In my view, there has long been sufficient evidence that heterogeneity of the environment and of the population itself is good for the stability and productivity of the whole system. So it is surprising to me, to put it mildly, that there is still a discussion about a choice between research quality and diversity. For the same reason, it is not very rational to keep an exaggerated focus on the tail end of the distribution of scientists in which reside the individuals who publish most, or who are the most cited, or who are the most award-winning individuals. The tail of that distribution does appeal to the imagination, but it can only exist because the rest of the distribution also exists. And that is just as important to the system. Therefore, to everyone I have ever worked or discussed with at all, in any way, the fact that I am allowed to stand here now is partly because of you. Thank you. In his absence, Professor Sloot, dear Peter, it is because of your confidence in me that the process for creating this chair gained traction. The collaboration has only just begun, but I hope and trust that we will achieve great things together. Mr. Holter, Dr. van der Hoeven, and Kranenburg, dear Joyce, Jacobine, and Marike, through your efforts, grand plans are put into action. I hope I can count on you in the future too, so thank you. I have been lucky enough to grow up in a family and a home that has always been a refuge, with older sisters doing their best to prevent my ego from getting too big. Not all of them can be present, even online, but at least I can still thank my mother and Evelyn from here for all the moral support all these years. My children help me to better understand the point of view of the students I supervise and to have more empathy. I hope they use their father's advice when it is helpful, but above all that they follow their own path. With children such as yourselves, it is ridiculously easy to be a proud parent. Thomas and Laura, thank you. It is no secret that Teresa and I have an identical level of education and even studied the same subject at university. That means that I am not only married to the woman of my dreams, but that I am challenged every day to explain what I think. I can trust she will tell me if I'm unclear or just plain wrong. If I do manage on any given day to be a slightly better person than the day before, it's thanks to her. Obrigado, meu amor. Ik heb gezegd.